Hey guys, this is Mrs. Ross. I hope you guys are all doing well. This is Precalculus section 3.5. And so we're going to talk about exponential and logarithmic models. Let me get my screen back up here. There we go. Oops. All right, so we are going to talk about 3.5. And 3.5 is an interesting section because it's kind of like, oh, we've actually got to something that we can use our exponential and logarithmic functions for. And actually within 3.5, there's two kind of unique sections. One is we're going to talk about the common exponential and logarithmic functions and what those graphs kind of look like, what we would expect for those. And then we're going to actually talk about going back to our compounding continuously, going back to our, sorry, I'm fumbling a little bit, compounding interest. And we're going to talk about how we can use the tools that we know how to solve exponential equations and apply that to compounding interest. So within 3.5, there's kind of two subsections, if you want to call that. So first up on my screen, we're going to tackle the first subsection of 3.5, which is graphing the parent functions for several of these logarithmic equations. All right, so up on my screen, you'll see my notes and you'll see 1 through 6 and some graphs on there. And I've pre-loaded these into Desmos so that you don't have to watch me type them all in. But we're going to talk about some of the common logarithmic and mostly exponential functions and what those look like. All right, so first I'm just going to run down the list here. You can see at the top of your page, we have, the basic models for a lot of our exponential functions as well as our logarithmic model. So the first two should look really familiar to you because we talked about these back in 3.1, which are exponential growth and exponential decay. So you'll see here that the distinguishing feature is that we have we have something to the x power. We have e to the x power and we have e to the negative x power. We have a b in there that it's getting multiplied by. But exponential growth, if you just think about what is exponential growth, you would expect something to start off growing slowly and then grow exponentially, right? So for an exponential growth model, you would expect it to look something like this. Exponential decay is just the opposite of that. Since we have a negative in our exponent, that we're going to start off at some really high value and then we are going to decay off into 0. So I think those two are pretty well ingrained by now with all of our exponential work. We have a common exponential function that's used a lot when we're modeling using standard deviation and doing modeling and doing a bell curve. So if you did any work with that in Algebra 2, it's called the Gaussian model. So a Gaussian model is actually unique. It has to do with the fact that we have x and that's a squared term, and then it's also negative. So we kind of get this reverse parabola going on. Remember, x squared graphs a parabola. So we get a Gaussian model. Since it's a negative of a parabola, we kind of get this nice bell curve exponential equation from a Gaussian model. And I think that makes sense to a lot of people. X squared parabola, we're kind of familiar with that. The one that we haven't talked a whole lot about is the logistic growth model. And what makes this unique is that our exponent is in the denominator. It's also negative. So if you have a logistic growth, and we haven't talked about these, we'll graph one, but a logistic growth looks kind of like this. We start off, we grow exponentially, then we decay back down. So we kind of just get this, a little bit of exponential growth, a little bit of decay, and it flattens back off again. And then our last one is unique because it's our logarithmic model, and it's our only one that has a log in it. So we have a common log and a natural log. It doesn't matter what it is. Any logarithmic function, remember, is just the inverse of our exponential growth. So if our exponential growth looks like this, then we would expect our logarithmic function to be the inverse of that, and it's going to look like this. All right, so that's kind of the high-level description. So now let's actually dig into these problems that are at the bottom, 1 through 6, and this is your homework. So if you have your homework sheet, you can follow along, or if you like to go back later and do the homework on your own, you can do that too. We are going to look at these equations, 1 through 6, and we're going to guess, not guess, we're going to make educated guesses about what model we think, A through F, we think best models our equation. So first off, we're going to look at number 1. So we have y equals 2 times e to the x divided by 4th power. All right, so to me, we have just our, this looks like our standard exponential growth, right? We have an x in the exponent position. It's not negative. It's kind of going to be our standard equation. So when I look at A through F, I immediately see C, and I say this right here matches to number 1 because this is exponential growth. This is our standard exponential growth. If I flip over here to Desmos and I turn that on, yep, we have our standard exponential growth going on, right? We have a little bit of change because we have divide by 4 and 2, and we talked about how that shifts the graph, but this is classic exponential growth, okay? So that matches up. Let's look at number 2. So number 2 looks really similar to number 1, except I have one change here, and that is that I have a negative sign in front of my exponent. So I have 6e to the negative x divided by 4. So because of that, that's going to tip me off that this is exponential, right? But it's not growing, it's decaying. And so that, to me, says definitely E. So 2 is E, which is definitely decay. Decay. So here we go, decay. And that's what shows up on our graph. All right, number 3, let's look at number 3. So number 3 is unique because it's an equation with a common log in it. So I know that the common log is, that any logarithmic function is the inverse of a exponential function, right? And it's going to look something like this number 5 down here. I'm between this being B and D, and the way that I can distinguish between B and D is you can look at some of my clues here. So I know that inside of my function, I have x plus 2. And since the plus 2 is inside my function, it's going to shift my graph to the left 2. And so this looks like my graph is shifted to the left 2. So I have a strong guess that it's B. But when I go to graph it, just verifies that yes, in fact, that 6 plus the log of x plus 2 matches this graph right here. So this would be logarithmic model. I think that makes sense, right? Okay, let's look at number 4. Number 4, we have our exponent, but our exponent is squared. Right? We have x minus 2 squared. So that tips me off that, okay, I know when I have x squared, I get a parabola, but it's a negative x squared, so that's going to flip my parabola over. And since I'm dealing with exponents, I have a pretty strong feeling this is going to be a Gaussian model or a bell curve, and my only bell curve is A over here. So number 4 has to be, I think, has to be my Gaussian model. So this is, let's flip that on, and there we go, number 4. All right, so we're getting there. Number 5, we have the y equals the natural log of x plus 1. All right, well, so they gave me another logarithmic model, and I was between B and D for my first logarithmic model, so I'm pretty sure this is going to be 5. And this makes sense too because I have plus 1, so I'm shifted down by 1, and I have my nice curve that looks like a inverse of an exponent. So there we go. That's our graph. And then last but not least is number 6 down here, right? And this is where my exponent is down in my denominator. It's negative. This is a logistic growth model. So this is probably the one that we haven't, logistic growth model. This is probably the one that we haven't dealt with a whole lot, but we know that we kind of get this component of growth and decay in the logistic model. It's also my last one left, so that's a good clue that I'm onto that. So I know that F would be 6, and when I graph it, I get my nice logistic model here. Okay, so that is graphing some different mostly exponential models and then one logarithmic model. This is just kind of a familiarity with what do you expect when you want this. If you you know, if you're talking about a logarithmic function, you kind of think, okay, that's the inverse of an exponential function, so I should be able to figure that out. So as I mentioned, we kind of have two sections in one. So 3.5, we have these models. Now we're actually going to switch gears a little bit, and we are going to go back to our compounding interest. Yay or not yay, depending on how you feel. So we did this back in 3.1, right? We talked about interest that's compounded over a certain period of time or that's compounded continuously. What we know now that we didn't know in 3.1 was we know how to solve exponential equations. So guess what we're going to do? We're going to use our knowledge from 3.1 plus our knowledge of solving exponential equations, and we're going to put those together to do some fun math. Fun, right? All right, so let's remember all of these problems here, 7 through 14, we're talking about compounding interest, and specifically, we're talking about interest that is compounded continuously. All right, so let's remember what that formula is. And the formula for continuously compounded interest is the current amount equals the principal times e to the RT. So it's PERT, right? PERT. Where P stands for the principal, R stands for the rate in a decimal form, and T stands for the time in years. All right, so this is our equation. And before, what they would do is they would give us the principal and the rate and the time, and we would just calculate the current amount, right? But since you guys are all smarter now at exponential equations and solving, we're going to get some different variables and see if we can kind of figure out how to fill in this chart. So what do I mean by that? So number 8, we have you're initially investing $2,000. This is number 8, right? That means that our principal is, so if I rewrite this, amount equals, our principal is $2,000. Know that to be true. Our annual rate is 1.5%. So we don't write rates in percents, they just look pretty. So we write this as 0.015. And we don't know what time period we're looking at here. Okay, so we have two things that we want to fill in here. We want to know, first off, what is the time that it's going to take to double my money? So to go from 2,000 of my initial investment to double my money would be to go to $4,000. All right, so what is the amount of time it's going to take to double my money? So what I'm looking at is I'm saying, okay, when is my amount going to be $4,000? If I start with an initial amount of $2,000, what is that time period that it's going to take to double? And when you look at this, what do you see? You see that your unknown, what you're trying to solve for, your time, is in the exponential position. And so that's where all of what we've learned from 3.2 through 3.4 comes into play, because now we actually know how to solve exponential equations. Before, we didn't know how to do that. All right, so we're going to go ahead and try to solve this equation and figure out how much time it's going to take to double my money. So the first thing that you want to do, remember, is you want to simplify using your other algebraic rules. And this makes sense, right? We're going to divide both sides by 2,000. So we want to know basically when it doubles, it means it's 2 times the amount, right? So 2 equals e to the 0.015 t power. Okay, so now we kind of have a more simple exponential equation, and we're going to use our skills. We have 3 strategies to figure out how to solve these. We can't really make this one-to-one because I don't really know how I'm going to make 2 and e the same base. So we're going to use the strategy where we actually change the exponent equation by taking the logarithm of both sides. And in this particular case, we're going to take the natural log of both sides because we have our Euler number here, right? So if I take the natural log of e to the 0.015 t power, okay, then by my inverse properties rule, these cancel each other out. This comes down to the front, and I get that 0.015 t equals the natural log of 2. And if I divide both sides by that number, I end up with the time to double is, let's bust out a calculator. I don't think I have it here. Okay, we have, no natural log on here. Bummer. All right, so I have to pull up Desmos. Desmos to the rescue. All right, the natural log of 2 divided by an interest rate of there we go. So it looks like our time to double is 46.2 years. Wow, we're going to be waiting a long time for our money to double. So our time to double is 46.2 years. It's going to take to double our money. Okay. The next fill in the blank that we have here is the amount after 10 years. This one should be a pretty easy calculation, right? So we have same formula over and over again. Amount equals P times ERT, PERT. Our principal is still $2,000. We have E, our rate is still 0.015 times 10 years. So this is just a basically plug in. If you plug all this in, looks like after 10 years, you're going to have $2,323.67. This one, I'm not going to take a whole lot of time. This is the same thing we did in 3.1. Just plug in and evaluate, right? Okay, so now let's look at number 12. Okay, so same idea. Right? Same idea. Number 12. Oh, my cursor's right on there. Our initial investment is $300, and they tell us what the amount is after 10 years, and we have to find out the rate and the time to double. All right, so let's figure out the rate first. So again, A equals PERT. That's an R. R. All right, so we know that the amount after 10 years is $385.21, that our principal is $300, and we don't know our rate, but we do know our time, the amount after 10 years. So rate times 10. Okay, so now we can, again, same process. We have our rate up here in our exponent. So let's go ahead and we're going to solve for R to figure out what the rate is. So first up, I'm going to divide both sides by 300. It's going to make a nice number for me. We're going to kind of leave it in that form. So we get 385.21 divided by 300 equals E to the 10R, right? Then I am going to get my R, my rate down, and I'm going to do that by taking the log of both sides because that's going to let my exponent come down. I'm going to be a little bit sloppy here, and I'm going to just smush it in so you don't have to watch me rewrite it all. All right, and so this is 10R. So on the right-hand side, we're left that 10 times R because the natural log of the Euler number is just 1, right? And our exponent comes down. 10R equals the natural log of 385.21 over 300. And my last step is going to be to divide both sides by 100. So if I do all this calculation, and I'll definitely switch to Desmos for this, and I have the natural log of 385.21 divided by 300 all over 10 years, I find out that my rate, right, is 0.025. That's nice. My rate is 0.025, or if we want to make it look pretty, 2.5%. So my rate here is 2.5%. Okay. And then if I wanted to complete number 12 and I want to find the time to double, how long is this going to take my money to double? Well, now I know my rate, and now I'm trying to figure out my time, right? So I want to know how long is it going to take my $300 to go to $600. That's doubling it. So $600 equals $300. This is my amount, my principal times E times my rate of 0.025 to the T power. This looks familiar, right? We're going to divide both sides by 300, so we're just going to end up with 2 equals E to the 0.025 T power. I need to get T down out of my exponent. I'm going to do that by taking the natural log of both sides. Again, I'm being a little sloppy here for quickness. And I will end up with the natural log of 2 equals 0.025 T. Divide both sides by 0. Of course, it couldn't be easy numbers, right? And when I do all that, I get my time to double is natural log of 2 divided by my rate, which is 0.025. My time to double is 27.7 years. So it's going to take me 27.7 years to double my money. Okay. All right. So 2 more examples and I'll send you guys on your way. Oops. All right. All right. So we're going to talk about compounding interest. All right. So complete the table for the time t necessary for p dollars to triple if interest is compounded annually at a rate of r. Create a scatter plot of the data. So now we're going to get even more complex. First off, let's think about this. What we're talking about is complete the table for the time t necessary for p dollars to triple if interest is compounded annually. So since we're doing annually compounding interest, we're not going to use our continuously compounding interest formula. We're going to use our other formula, which is that the amount equals the principal times 1 plus the rate over the number of times that it's compounded times the number of times time. All right, so this is our value. So let's kind of go back and fill in the blanks here. We know that interest is compounded annually. So because it's compounded annually, we know that n, the number of times per year it's compounded, is just 1. So that simplifies our equation a whole lot, right? So let's rewrite this when n equals 1. So we have the amount equals the principal, 1 plus, and then this is just r over 1. So 1 plus r to the t power. So that helps out our equation a lot, right? So what we're looking at is how long does it take my principal to triple? So really what we're saying that when we want to figure out how many times is when the amount is 3 times the principal, right? So we're trying to figure out how many times it triples. So if I put in here that when is the amount 3 times the principal equals the principal times my exponent. So we're just doing a little pre-work before we even dive into the numbers, right? Then I can divide p by both sides. So basically we're trying to figure out when is it 3 times 1 plus the rate times time. All right, so this looks a whole lot of easier to kind of deal with than what we started with. We're looking for when it triples. We know that our interest is compounded annually. And so that kind of simplified our equation. So we're kind of left with this equation here. And so that works out nicely because they give us a little table to fill in, right? Where we have our different rates and then the time that it takes to triple at that specific rate. Okay, so we are basically trying to solve for t on different values of r. And t just so happens to be an exponent. And we just happen to be experts in exponents right now. So let's see if we can solve this equation for t. So right now t is in the exponential spot, right? And we know that if we want to get something out of the exponential spot, we're going to take the log, basically the opposite of exponents, to be able to do that. So you can pick any function, but let's do the natural log. So let's take the natural log of 3 and then take the natural log of 1 plus r to the t power. And this makes me happy because my t goes down to my front, right? So this becomes the natural log of 3 equals t times the natural log of 1 plus r. So we're trying to find a function that solves for t at these different values of r. And I'm running out of room, but I can add more space on here. Oops, not what I wanted to do. Add some more space there. There we go. All right, so now if I divide both sides by the natural log of 1 plus r, I come up with an equation off to the side that looks like this. I get t equals the natural log of 3, remember, because we're trying to figure out tripling, over the natural log of 1 plus r. Okay, and we just so happen we have a table that we want to fill in, right? And we have different values of r that we want to evaluate this this function for. So now is where we want to switch over to some type of graphing tool. So let's switch to Desmos. I think we can get rid of all these now. So what we're going to do is we're going to say, I don't know if it'll let me do t in here. Let's see. T equals the natural log of 3 divided by the natural log of, nope, got to type it in right, natural log of 1 plus r. All right, and we want to evaluate for different values of r. So what we want to do is we want to take this and we want to turn it into a table. No. Oh no, that's not what I wanted to do. Undo. Oh, good. Done. Okay. Nope, can't do that. Oh, I keep wanting to hit undo. What if I put this in terms of y and x? So we're just going to know that this is my y and this is my x, and then maybe my, there we go. Now I can actually make a table out of this data. Okay, so I want to know when I put in a rate of 2%, which is my, my x in this equation, how long does it take for me to triple my amount? So if I put in a rate of 0.02, because that's 2%, right? It takes me 55.4 years to recoup, or not to recoup, to triple my original amount. So to go from, $100 to $300, it would take, at an interest rate of 2%, it would take 55 years. So then let's just keep filling in this table. So at a rate of 4%, it only takes 28 years. At a rate of 6%, takes 18 years. At a rate of 8%, takes 14 years. 10%, if anybody finds 10% interest rate, let me know. I will go find it. Or 12%. Those would be great, right? So here we go. This is actually the same as this, where the X represents our rates, and then this represents our time to triple our value, okay? If I make this a little bigger here, one of the things they asked us to do was to create a scatter plot of the data. So we have this on here, but we need to like clean it up a little because our x-axis should really only go between like 0 and 0.2. And our y-axis should go between 0 and 60 years. There we go. That's better. All right, so here's a scatter plot of our data, right? So this just shows you if you have a low interest rate, then it's going to take you a lot longer, to triple your data. The higher your interest rate, the quicker that you're able to triple your initial investment. Okay? All right, so one more problem and then I will send you on your way unless my computer dies and then you're done. Okay, so last one is population. We're going to use exponential models to model population. I think this is a really interesting problem. Something that you can actually visualize. All right, so the population P in thousands of Las Vegas, Nevada can be modeled by P equals 258 e to the k t power. That's really hard to see. Where t is the year with t0 corresponding to 1990. In 2000, the population was 478,000. Find the value of k for the model, round your result to 4 decimal places, and then use your model to predict the population in 2010. All right, so we have a model. Population in thousands equals 258 e to the kt power. K represents some constant, t is the time. So they tell us that when t equals 0, that's 1990, okay? And they also tell us that in the year 2000, I'm off the page, the year 2000, which is 10 years later, so when t equals 10, the population is 478,000 people. So we know that when t equals 10, the population when t equals 10 is 478,000. Okay. One thing that you have to note, though, is that the population P is modeled in thousands. So we actually will take off our thousands portion and we'll say the population is 478,000 because it's modeled in thousands. So we actually have the the population at a certain time, and using that, we should be able to figure out what our value of our K is. Excuse me. All right, so we know that in 2000, the year 2000, the population is 478,000, and that equals 258 E. We don't know what K is, but we know that the time is T, or the time is 10 years in. All right, this looks like a exponential equation that I know how to solve now, right? I'm going to divide both sides by 258. And I'm going to leave that as my crazy fraction here. Okay, and then I end up with e to the 10k power. How am I going to get k down and solve for it? Well, I'm going to do the same thing I've done all the time. I'm going to take the natural log of both sides, my sloppy way, and that's going to, this is the inverse of each other, so they cancel each other out. And I'm going to end up with an equation that says the natural log 478 over 258 equals 10 times k. I'm going to divide both sides by k, and when I calculate this, I'm going to come up with what is my k, my constant. So thanks to Desmos, we have the natural log of I gotta find my equation here. Oops. The natural log of 478 divided by 258, right? Oops. All that divided by 10. All right, so I get my constant is 0.617. Okay, equals 0.0617. That's my constant k. So then if I wanted to, so now I know my model, what value of k is. If I wanted to predict the population in 2010, I'm going to find out, all right, when time equals 20, because that's 20 years out from our original date of 1990, what is the value of my equation? What is my population? So the population equals 258 E times my constant, which is 0.0617 times 20 years. Running off the screen, sorry. All right, so when I plug this in, this is just a simple calculation, right? Plug this into Desmos, I get 258 times e to the 20 times 0.0617. Oops, not an and sign in there. So it looks like the population in 2010 would be 886, which is 886,000 would be my population. All right, guys, thanks for sticking with me. I know that was a long one. You should be able to do 3.5 now, and I will talk to you when